We need to move on to our next speaker, which is Terry Bauer from the Department of Biological Sciences at Idaho State University. Terry is a professor in the department. He joined faculty in 2004 following 18 years at the Institute of in Wildlife Biology at the University of Alaska in Fairbanks. He's a fellow of the American Association for Advancement of Science, the Arctic Institute of North America, and the Wildlife Society. His research interests include ecology, behavior of large mammals, and has published extensively on sexual segregation and birth site selection in ungulates. So, Terry?
Well, I'd like to thank Paul and the committee for this opportunity to talk with you, and I now see I should have had the wit to find a different order of presentation because that's going to be a tough act to follow. What I hope to accomplish today is to talk about what I think are traditional views of interactions between plants and large herbivores, the feedbacks of those systems, in particular on the population dynamics of large mammals, and then I'd like to suggest where I think we ought to go and maybe some information from our knowledge therein that might inform management actions. I'd like to start by acknowledging my co-authors Kelly Stewart and John Key. So, how are herbivores thought to influence vegetation? The traditional views are, of course, they remove species from the environment. They alter competitive interactions among plants that are there, thereby influencing the species composition. There can be trampling and compaction of soil, which has effects, and then in severe cases, of course, there can be erosion. Now, here's an outcome from the Starkey experimental forested range that showed many of those effects. I'm not going to say very much about Starkey because Marty Vavra and Kelly Stewart are here. We'll be talking about it. I'll just say that it's a huge area with elk-proof fences that's amenable to some really unique manipulations of herbivore density. Here on the 20 elk per square kilometer side, you can see many of those interactions that I talked about. There are areas where it looks like someone hired a bonsai gardener to go in and trim up all the shrubs and trees. So this is sort of a classical outcome. So this is a model that served us well for many years, looking at the effects of grazing intensity on range condition. And there's a couple of things about this model that we now know don't work so well. The first is the notion that we can ratchet this back and forth and change the range condition. We now know there are states that you can arrive at that aren't immediately amenable to reducing grazing intensity and provoking change. But what I want to concentrate here on is the decreaser. These are the highly palatable forages that herbivores eat. And you can see that these traditional models cause them simply to decline with increasing intensity of grazing. So what else do I think are important about interactions between plants and large herbivores? First, I don't think you can work in this field without appreciating the unique life history strategies of these large mammals. We need to know a lot about the role of plants in the population dynamics of herbivores, and in particular, the feedbacks that occur therein. I think that new and emerging ideas about herbivore optimization and nutrient cycling have value to land managers. I believe that we can do single species management and bring about shifts in biodiversity. And then I'd like to talk about other factors that influence the distribution of large herbivores on the landscape and the feedback of those distributional changes on these other processes. So, as I pointed out, these animals have very unique life history strategy. Compared with other mammals, they have very large body size, they're long-lived, they tend to delay reproduction. With comparison to most mammals, they have a small litter size. There's very high maternal but not paternal investment in these animals. They are superb competitors, and all this leads, all these life history characteristics lead to the key. They have extraordinarily strong density-dependent feedbacks in their population dynamics. And the failure to comprehend that can lead to some management disasters. I want to point out that knowledge garnered from small mammals simply may not be applicable to large mammals because of these unique life history characteristics. And I'm going to steal the title from an old paper that I really like by Colley and Krebs, and that is Big Mammals Are Not Simply Small Mammals Writ Large. And if you haven't read that, I would encourage you to have a look, because it was a keystone in the change in my thinking about these species. Okay, so the key here is that the food supply of these animals influences their physical condition and thereby their reproduction. This is more Starkey data. It is a density experimental manipulation, so you have increasing elk density on the x-axis up here. You have depth of runt fat, a good measure of physical condition. You can see it declining with increasing population density. And here you have the portion of animals pregnant, and although it's noisy data, they decline significantly as well. By the time density-dependent effects cause a decline in pregnancy rates, you've already seen in most circumstances declines in survivorship of young, a lack of recruitment, as well as lowered survivorship of adults. Now, I wish it were this simple, but it's not, because the age structure of the ungulate population also plays a role in this. Here's aging years on the x-axis, proportion of females pregnant. Here's that 20 elk per square kilometer treatment. Here's 4 elk per square kilometer. You can see that the major differences in pregnancy rates occur here only at prime age, and then both become senescence. And of course, I'll caution that that's anchored by relatively few data points. So you need to know something about the age structure of the population as well as their density to understand these density-dependent relationships. So, probably the most important feedback is that you see with increasing density a decline in per capita availability for forage. And remember, I said these animals are extremely good competitors, and that high density may cause the population to crash. These are data from Dale McCullough's George Reserve deer herd. The data are smooth, but they make the point. We have a population eruption, an overshoot of K, a crash, and then recovery with a potential loss in carrying capacity in this process. And there's two things I want you to note here. This model assumes that K is constant, something I'll come back to later. But also, note the size of the overshoot relative to the crash. You get a very small overshoot and a proportionally large crash, and this has been demonstrated empirically on a number of occasions. So what's going on here? This relates back to the population dynamics of deer. Here you have the recruitment of young into the population against the population size of deer, and what I've drawn here are 3 recruitment parabolas for a population with a carrying capacity of 600, 800, and 1,000. Here are the areas underneath those curves, and now watch out, I switched the axis here, so a K of 1,000 up here and a K of 2,000 down here, but as K is reduced, the area under those parabolas declines in a nonlinear fashion. And what this means is 2 things. A small change in K may precipitate large change in herbivore numbers, and net annual recruitment of young is reduced disproportionately to the decline in K, and that's why you get these precipitous crashes following overshoots. Now, the other thing that I didn't talk about is the resistance and the resiliency of the community, and that is coupled with the population dynamics of the animal to look at the rate and the amount of recovery. So it may well be that these overshoots can cost you carrying capacity and set up a new series of population oscillations. But the point is here, you need to worry about what plant community you're in, as well as the dynamics of the animals that you're concerned with. So there are other effects of high density. These are data from the San Bernardino Mountains of Southern California. This is a principal component analysis of dietary niche, and I want you to concentrate here just on principal component 1, which is a browsing to grazing axis. We have 2 paired sites that are very similar in habitat. One at low population density. This is a centroid with 95% confidence limits and represents the niche, the dietary niche of that population, and you can see it's composed of most grasses and forbs. This is a high density site. You can see that the size of the niche is very small and is constrained to a few species of browse. And what's happened here, that these density differences have been maintained over time, and this population long ago eliminated all the forbs and browse. And so you can imagine, if you want to look at ecosystem processes, these things are about 7 kilometers apart, that what's going on here is just markedly different than what's going on here. So rather than a clinomatrix, which I showed you before, there are these states in which herbivores and what they eat can differ markedly based on their population dynamics and intra-specific competition. So it's even more complex. This is Perry Barbosa's gastrocentric model here. And what I want to contrast is the morphology and physiology of a large male. These animals are highly sexually dimorphic. Males have absolutely larger rumens. They require absolutely more forage, but because fermentation times are longer, they can handle much lower quality forages than can females. Down here, we have a reproductive female. She's completely remodeled her digestive tract to cope with the needs of pregnancy and lactation. It's not shown here, but we now know that she increases rumen size and number of papilla. She increases the size of the liver, the small intestine, the cecal proximal colon, and this is necessary for her to ingest the high-quality forage necessary to support lactation. So you have animals with radically different morphologies and digestive efficiencies, and this results in them partitioning space on the landscape. These are data for mule deer in the Cuyamaca Mountains of Southern California. I want you to look here first. This is a period of sexual aggregation. There are dry eastern meadows at low population density, wet western meadows at high population density. You can just see from the number of samples, but the relative proportions of males to females are near identical. During the period of parturition, when these different needs emerge, over here on the dry meadows with plenty to eat but of low quality forage, males are in abundance and females are less abundant. Here on these meadows where females require really high nutrition, you can see it's predominantly females and relatively few males, and the process is known as sexual segregation. This is another manipulation done down on the Welder Wildlife Refuge in Texas by John Key, and this is an actual manipulation of deer density. So we have deer at moderate density in white here, and we're looking at the proportion of quadrats on which they were sampled that were sexually segregated. And so you can see that sexual segregation actually peaks around parturition, which is exactly what we would predict. Now we allow one part of the population that's separated from the rest to attain quite high densities, and I'm not going to talk about how here, but you can see the degree of sexual segregation is constrained markedly. This has a huge effect for diets. Another principal component analysis showing dietary niche breadth, just concentrate up here. This is the moderate densities where there wasn't much spatial overlap. They were segregated, and you can see the dietary niche of females is completely included within that of males. Now, we'd always expect males to have a somewhat broader dietary niche based on their digestive morphology and physiology. Now we perform the density experiment where there's far less overlap, and notice that the diets of males and diets of females completely diverge. They're acting as if they were separate but coexisting species. Standard niche theory. Overlap on one niche axis results in separation or avoidance on another. And so these simple shifts in density have huge effects on the diets of the animals as well as their spatial distribution. So in the mid to late 1970s, Sam McNaughton and Roger Roos and their colleagues began working in Serengeti grasslands. And what they found was that as we increased grazing intensity, net above ground and primary productivity increased. But the interesting part is that with no or little grazing, NAPP was quite low, as it was out at very high grazing. And here at low to moderate densities, you see mass increases in NAPP. And it was thought that you needed large herds, concentrated grazing activities, and inputs of feces and nitrogen and urine back into the system. And this was only a property of grassland ecosystems. Here's an example of a Serengeti grazing lawn with wildebeest, but those occur in North America as well. This is a bison prairie dog grazing lawn, where bison preferentially feed on prairie areas with prairie dog colonies. You can see the standing crop of vegetation here is quite low, but what you don't see without experimenting is that the productivity of these areas is exceptionally high, as is the offtake by herbivores. So we began wondering whether these kinds of properties would work in other ecosystems, such as boreal forests, and whether browsers could be involved in the process. This is a study near Fairbanks, Alaska, and what we're looking at here are browsing histories of willow stems over a 2-year period where neither year it was browsed. It was browsed in one year but not the other, and then it was browsed in both years, and you can see that the biomass of those stems is huge. And two things are going on. Of course, moose are feeding on larger stems, but by browsing, as you can see from this to this, they actually enhance the size of the stem that regrows. This is more of the same sort of data again near Fairbanks. Here we're looking just at twig diameter. So we measured the bud scale scar. That's the point from which this way is all current annual growth. The diameter of that, and then the diameter of the bite. And note that these bites are down around 2.5 millimeters. And what you see is that moose are returning to areas where there are bigger bites and taking slightly larger ones when they do so. More, at least, preliminary evidence that maybe something's going on in the boreal forest. So then this is from the Kenai Peninsula, but it's a similar idea. We're trying to look at the age of the stem, 1, 2, or 3 years old, on its quality. Here we're looking at percent nitrogen, and you can see a decline in percent nitrogen in the bite if they bite back into older vegetation. And we're also comparing both large and small stems. And then for digestibility, the effect is more pronounced for large and small stems, but there's almost an age-related factor there as well. So if you bite back too far, you're getting a poor bite. Now, what about nutrient cycling? Remember, this is the other key issue relative to herbivore optimization, and one of them that McNaughton and Roos noted. And this is for Denali National Park and Preserve. And just concentrate here for a moment on rates of nitrogen mineralization. And when I say high density, this is a bit of a misnomer. This is a population held at extraordinarily low density by wolves and bears, so that the overall population density is about 0.4 moose per square kilometer. But at higher density sites, you can see there's greater overall rates of nitrogen mineralization than at low density. And this is another piece of the puzzle to suggest that perhaps herbivore optimization might occur in other types of environments that aren't grasslands. So now here's the real evidence. We're back to Starkey again. This is the population density of elk plotted against net above ground primary productivity. The open circles are exposures, zero herbivory, and then there's a low density and a high density treatment that we discussed previously. We get a parabolic function, but look way up here. Look at low density at the amount of net primary productivity compared to no productivity at all. If we compare that against offtake, it's an identical pattern. So these animals are benefiting from the enhanced production of forage in this ecosystem, and it's not a grassland. In addition to that, we can look at net above ground primary productivity in relation to species diversity and species richness. The data are noisy, but both of these lines are significant, and what that suggests is NAPP is the key to diversity in these ecosystems. When we use a structural equation model to look at these pathways, and Kelly has a poster on that, so I'm not going to explain this in detail, but the bottom line is that population density affects NAPP, which is in turn affecting plant species diversity. This relationship right here was extremely non-significant. So what else is going on? Well, another potential factor that affects the distribution of animals and their grazing and browsing activities on the landscape is predation risk. These are data for moose from the Kenai Peninsula in Alaska. This is a selection ratio here. And here we're looking at distance from escape cover. 4 primary winter forages. You can see strong avoidance of black cottonwood here. When we move out further from cover, where there's greater predation risk from coursing predators such as wolves in the wintertime, forage preferences disappear, and they eat black cottonwood in proportion to its availability. And you can imagine that these small differences over relatively fine spatial scales are going to have impacts for our understanding of herbivores on plant communities. Here's another example from Denali National Park and Preserve. Here we're looking at the bite diameter of the stem of willows. Here we have the dense boreal forest moving out into open tundra. And what you can see, if you remember previously, in the forest, they're taking bites where they're getting mostly current annual growth, if you remember that previous slide. As we move into open tundra away from cover, you can see one massive increase in the variability, but also in them taking some bites that certainly go beyond current annual growth. And so the point is that their forage selectivity declines with enhanced predation risk from coursing predators such as wolves. and in this case, grizzly bears. What else is there? This is an example from St. Elias National Park with female caribou during the period of parturition. Here are female that have just given birth or that have calves and the elevation at which they move to do so. So they're moving to high elevation sites that are generally beyond the elevations used by both grizzly bears and wolves. Okay, forage there is sparse. If they lose a calf or if they're non-pregnant, they immediately drop back down here to lower elevations where there's more forage, and the males remaining down at forage at low elevation levels where forage is plentiful, probably because compared with young, they're far lesser risk to these big carnivores. These are data for an endangered population of bighorn sheep in the Sierra Nevadas, and I want to begin talking now about the differences between the sexes and their response to the various environments. So here we have foraging efficiency, which is the percent of active time spent feeding, and the effects of group size on that. For males, up top here, you can see, although it asymptotes a bit, that foraging efficiency is enhanced with increasing group size. For females, there's no such relationship. So what's going on there? If we look at distance to escape terrain, there's absolutely no relationship between that and foraging efficiency for males, and they'll move far out away from escape terrain where there's plentiful forage. If you look at females, look at the strong negative relationship, so they won't even go more than about 50 meters, and even then their foraging efficiency is declining. So because females and their young are far more susceptible to predators than our large males, it affects both their spatial distribution and their foraging activities and the amount of time they have to feed. This is an example of mule deer from the Cuyamaca Mountains of Southern California. Here we're looking at group size, as we did before, against the activity of deers. And not surprisingly, as you've seen before, that as group size goes up, the percent time feeding increases, and the percent time spent in alert alarm behaviors declines. So here's an effect on the landscape of a shift in feeding activities with respect to group size. It's more complex, as all things are. These are activities of deer again from the same population, but now these are lone deer only in meadow ecosystems. Again, distance from concealment cover out here, and you'll see here that about 30 meters from concealment cover you see maximal foraging and minimal alert alarm behavior. If you move on out here to about 80 meters, you see a minimum in feeding and a maximum alert and alarm. These data are just noise from small sample sizes. There's not too many areas where deer can get that far from cover in this system. Well, our hypothesis is this. Notice here close to concealment cover at about 10 meters, there's actually low feeding and increases going up to 30 meters, and then an actual decline in alert alarm behavior. Well, you've got a stalking predator working the edges of these meadow systems, and they're effective at about 10 meters range in a rush at a deer. So they stalk along and make a quick rush, and so here close to cover, they're worried about those stalking predators. Out here you have an important coursing predator, the coyote, and as you move further and further from escape cover, they become more and more sensitive to those different levels of predation, so that types of predation can affect the foraging dynamics of animals on the landscape. These are Starkey data again from Kelly Stewart, and they demonstrate something that no one has previously done. What Kelly did here is an example from just 1 year. This is the density manipulation here. This is the low density site. This is the high density site. These are Krieg values of density. The little black dots are exclosures in the system, and this is that same relationship for males. And you can see first that males, because these things are polygynous, are occurring at much different densities. The proportion of males in the population is naturally low, and so just putting all out together in one category is a mistake. And you can also see that even though we've done high and a low density manipulation, animals are not distributing themselves equally across the landscape at all. Until you begin worrying about these sexual differences in distribution, you're liable to miss important information about the way these big mammals forage. Here's another example from the San Bernardino Mountains of Southern California by Vern Blythe. Now, these bighorn sheep actually spatially separate, the sexes do, from one another in mountain ranges that are 15 kilometers apart for about 8 months out of the year. So what's unique about that? There are 3 different methods here of measuring the abundance of predators, feces per hectare along transects, and every time I do one of these studies, I swear I'm not going to pick up feces again, and inevitably it happens. These are predators in frames of film at water holes, and then these are observations made from aerial sampling with a helicopter, and you can see these male ranges predominate in terms of the number of predators present. If you think about this, males are occurring at low density. They're willing to move far into open areas where it's more dangerous and there are more predators. Females are occurring at much higher densities, but using areas where they're less vulnerable to predators, especially their young. And so this kind of a patsy distribution has to have an effect on plant-animal interactions. But frankly, it's poorly studied. Again, Kelly's the only one that I know that's even attempted it. So what's the future look like, and what else do we need to worry about? These are data that are in review from Becky Pierce. This is Round Valley in Central California in the Owens Valley. And this is a long-term study of mule deer and mountain lion dynamics. The number of mule deer here, the number of mountain lions here. And we didn't have line data for the whole time interval, but we do have peripheral information not shown here to suggest it was high during these periods. And what we think happened was there's overshoot of carrying capacity here. The population started to crash, as I showed previously. We hit an incredibly bad drought that brought the population down to very, very low density. During this period, they were eating a poor quality diet. Their physical condition was low, and the pregnancy rates and recruitment of young were really quite poor. The drought ended, and almost coincidental with the start of the mountain lion study. Here you can see the mountain lions remaining very high. Now these scales aren't the same, so don't let that fool you. There can't be more mountain lions than mule deer, obviously. But it came crashing down with a long time lag, tracking the deer down. We know from another study by Jeff Millipeak they did not prey switch. They maintained mostly mule deer in their diets during this crash. And so what you see here is a lambda of 0.76. And a crashing population, but then the mule deer population begins to recover, even though mountain lions are coming down behind them. Here, we're seeing an increase of about 10% a year. Female condition is good. Twinning rates are high. Survivorship of young are better. But a 10% increase per annum is just a little more than half of what mule deer are capable of. And these data are at least suggestive that we're seeing top-down forcing. So here we have sort of unequivocal evidence of bottom-up limitation due to an overshoot and drought. And here, as the population should be recovering more quickly, the large number of mountain lions in the population are holding them down. This occurred in a relatively short span of time in the same population where we're inferring bottom-up regulation and then at least a strong component of top-down regulation, all with concomitant effects on plant-herbivore interactions. Their diets change markedly during these 2 periods. Now we also know that these kinds of changes between predators and prey can lead to trophic cascades, and since you're going to hear about that from Bill Ripple tomorrow, I'm not going to go into that. But it suffices to say that we know these things can not just affect plants, but have an effect on birds, on rodents, on terrestrial and aquatic insects. So there can be profound ecosystem effects from the kinds of changes you're seeing here in a particular population. And the dogma that top-down and bottom-up is a dichotomy based on this is way too simplistic to describe these complex predator-prey interactions. What else is important? We're back to the George Reserve in Michigan with a density manipulation on white-tailed deer performed by Dale McCullough. The y-axis here is the number of young per adult successfully recruited to the population, i.e. the recruitment rate. It's not a parabola here. And then the size of the population following hunting. And Dale fit a couple of regression using various categories of females. And you can see as population density goes up, recruitment rate declines. And this is a classic density-dependent response. When Dale added males to the equation, though, the relationship became non-significant, and indeed males only accounted for about 18%, about 18% of the variability in recruitment rate. Well, how can that possibly be? Because deer aren't just deer, they're sexes of deer. I showed you previously that the sexes of these animals partition space or diet, especially associated with the period of parturition. And what this really means here is females that are principally competing with other females and their young that are affecting recruitment rates through physical condition, pregnancy rates, and other factors, where males here have avoided competition with both groups and, at least at high densities, have a relatively strong or relatively minor effect on recruitment rates in this population. That's not to say that males aren't important. If we don't have males in the population, we don't think we're going to get baby deer. What it really means is that relative to the population dynamics, especially at high densities, their contribution is relatively unimportant compared with the nutritional condition of females. If you solve nutritional condition, then there are data suggesting the presence of males can affect things like timing of reproduction, estrus, ovulation, and so on and so forth. But from a practical management perspective, it suggests that they're not that important. So if you'd like to garner some of the benefits that I've shown you in these other slides, it may well be that agencies have to rethink some of their harvest management strategies for large herbivores to include more females, because you will not be able to drive the population back to the low densities where we showed herbivore optimization and it enhances in biodiversity by harvesting only males. It can't occur because these animals are behaving as if they were separate coexisting species. They're partitioning space and or diet, and the ability for them to compete with one another is minimized, and so it's principally female-female competition that are driving the population dynamics. So if your goal would be enhanced biodiversity or productivity of the deer population, then I think most management, in particular in Idaho, where females typically are not harvested, those options are nil. Okay, I said I'd return to this, and now I intend to. And what we're looking at here, again, data from the George Reserve. This is through a period of about 24 years, a population, eruption, an overshoot, a crash, and a potential loss in carrying capacity. And I said that this process right here implied that K had to be changing, not static. Now, we've known that this isn't possible for many, many years, but the population models, even those by Sinclair, propose to adequately model changes in herbivore populations and changes in vegetation are poor only because they don't seem to be able to cope with this really steep eruption and then the subsequent crash. If you look at those models, they're kind of rounded and smooth and flowing, and we know empirically that that's not the case. Well, here's where I think we need to go. I think that this is a reasonable representation of what herbivore optimization and loss of K might really look like. The population, as the herbivore population increases, obviously there's got to be more K out here somewhere to support them before they begin to reduce it. We see a little bit of herbivore optimization at really low density, which is responsible then for the steepness of this eruption, the overshoot of K, the lag, and the recovery. And I think this is an area where we really need to have more research. We don't understand this at all. We don't understand how different plant communities respond to this. It could be with secondary compounds that Fred spoke about. There's lots of reasons why K might be lost or not, and how the plant populations are going to respond to these changes in herbivore density and numbers, but it needs to be done in concert. You can't do one without the other. You need to know something about the population dynamics of the animals, and you need to know more than we do about the nature of the plant communities and how they interact with one another. So if I were going to suggest somewhere where we really need to do a lot of work, this is the area, but it's hard to do without an experimental approach. You can't sit around on your hands and wait for a population eruption and a crash. And that's why areas such as Starkey, where these kinds of manipulations can occur experimentally, are so important. So, am I going to finish early? So no questions. We can have, where we have keystone species, we can have single species management to manipulate biodiversity. I don't think there's any question. I think that's in the can. And if you're asked to go out and manipulate the ecosystem, I think you all know how difficult that could be in terms of writing some sort of prescription. So if you're willing to have these animals at relatively low density compared to their current densities in most areas, especially those without predators, then it is possible to do this. But on a broad scale, it will change. It'll require changes in most of our existing laws relative to harvest of animals and their sexes. We really need to work on models of population dynamics to more fully incorporate herbivore optimization, and that needs to include some information on the resilience of these plant communities and how they respond. John Bryant said long ago that you could grow slow and defend yourself, or you could try to grow out of reach and be nice and palatable when other things eat you, or you could grow thorns, for instance, to try to avoid herbivory. I don't think we know enough about that, and I think that interaction is a critical one. And then I think we need to better understand factors that affect the distribution of large herbivores. I think I demonstrated pretty unequivocally that predation risk can affect the distribution of animals on the landscape, and that differs by sex. Despite a bazillion publications, I don't think we understand sexual segregation. There's an ongoing war in the literature, even over its definition. Perry Barbosa noted in 2000 we don't have a functional definition for the process. That is an ongoing problem, even though I've tried 3 or 4 times to fix that, unsuccessfully every time. And then the next step is their effect on ecosystem processes, and I think that's where the future lies. Thank you.
We have plenty of time for questions.
I was afraid of that.
Fire away.
Yeah, down here in the front.
Do you know how a grazing-induced change in above ground primary production would translate to a change in the below ground primary production?
The question is how does the above ground production and the below ground production relate to one another? Roger Roos has done a lot of work on that, and you see concomitant changes in both. In fact, there are far greater changes in root biomass than there is in above ground productivity, just as I suspect you understood before you asked the question. So yeah, both of those are going on, and you know, doing this nutrient cycling stuff is a lot of hard work. It takes a lot more samples than you usually put in. It takes, you know, you've got to be really cautious with it to get matched areas and everything else. And so, if you're going to do this, you need a tame nutrient cycler to help you do it. Anybody else? Sure, why not?
Do you know what would be the main mechanisms for increasing carbon sequestration in soil on the grazing? Would there be an increase in the ground?
That's a good question. She's asking what happens with carbon sequestration, and you see enhanced respiration. So I would assume that would lead to enhanced sequestration. But I would go back and look at some of Roger Roos's recent publications. I think I'm right, but I hate to shoot off the cuff like that because I'm extrapolating. I'm free.
Other thoughts or comments, and if you have one here.
I'm sorry.
Terry, your graph of mule deer and mountain lions in California, I believe, why did the mountain lion population not level out or increase slightly as deer populations increased? It seemed to be still going
there was a horrible time lag first, okay, that we don't fully understand. I think you're looking at a residual from them feeding entirely on mule deer, okay, and the mule deer population having crashed and then continuing on down. I think when we get the next 10 years of data, you'll see the recovery. The problem is now is that that's where those endangered Sierra Nevada sheep live. And if a mountain lion even looks like it's going to touch a sheep, it's eliminated from the population immediately. And so it's very difficult now to assess that. I said we had previous information the mountain lions were high. Those were depredation permits, and I didn't present those data. So they've even exceeded that now to protect the sheep population. That's one of the rarest large mammals in the world. It got down to as few as 100 individuals. It's up to about 300 now. And it's the source population for all the translocations for the Sierra Nevada, and they don't feel like wasting a sheep. So if a mountain lion whacks a sheep, it's gone. So it makes it hard to interpret.
We have a little extra time. I'd like to encourage you to ask questions of Fred Provenza as well. Anybody over here?
Brad, you talked about the invasive plant species that come in and so forth, and then be able to embrace those in theory. Let's talk about cheatgrass for a minute. And just cheatgrass and there's been words about war on cheatgrass and so forth. And how can we utilize grazing to help address that issue, I guess? Or is work from your perspective, is it an issue, or do we need to embrace cheatgrass as part of the system?
The question was about cheatgrass and my comments that we need to learn how to love these invasives to death. My view on cheatgrass is that I'm not particularly fond of it because of the way it grows in monoculture. Its poor ability to maintain soil integrity, which I think is the basis of systems. It sets up fire regimes that aren't good. So I think people are doing work that shows that you can use livestock grazing to start to work with that. So, yeah. And when I say embrace invasives, the idea is that maybe they'll live with them, but in the case of cheatgrass, see what you can do to work with that and move it, in my mind, toward more perennial plants, good ground cover, soils. Tara's talking about nutrient cycling and all those things, and couldn't agree more with the things you're talking about, Tara. But I'm really impressed with the work that a number of livestock producers are doing nowadays related to integrity of ecological systems and building that integrity from the ground up, and that means soil, plants that hold soils in place, and biodiversity. So I'm all about that. Does that make sense? So I'm saying it's going to change, and so we better embrace it, and we better figure out how to work with it.
Yes. Down in front here.
Yes, so you talked a little bit about that foraging selectivity declining as risk of predation increases. So how do you tease apart whether or not these animals are willing to be riskier because of their quality food farther away?
Right. So the question is, how do you know that they're incurring a greater risk to move or forage farther away? And the best study of that was done by Joel Berger, in which he actually supplemented food at greater distances from escape terrain for bighorn sheep. And indeed, they did exactly that. They took the risk, but the males did so in larger groups, and they spent more time in alert or alarm behavior. So you could actually provoke them to move further from cover. And then Mark Hebblewhite has been doing some forage selectivity studies in which he puts food in with things that aren't food and looks and see what kinds of things might keep the animal, looking at giving up densities. And with these large herbivores, apparently there aren't any. We have similar data for bighorn sheep, and they're willing to take any risk to get to a high enough quality forage, and you can move them anywhere to do it. So a little bit contradictory in that regard, but I think that forage can be so important it can override other components of the system. But predation risk is important. In Alaska, where moose populations in Denali Park are held at incredibly low density by a combination of bear and wolf predation, and where you have multiple prey to allow those animals to switch off when moose populations become low, the impacts are profound. Animals are in beautiful physical condition. Survivorship of young is nil, and they get really big. A big cow moose will be 1,100 pounds, a big bull 1,700 pounds in those systems, where there's relatively unlimited forage availability because populations are depressed by predation. Those are guidus. That's a different subspecies in here. The Shiras moose is the smallest of the subspecies in North America, and they never get that big. So don't be too deluded by that.
Question or comment for either Terry or Fred. Seems like repeatedly in terms of aspen shoots and reproduction in central Utah, we see situations where one area, perhaps one genetic clone, is eaten vociferously, and just up the road, a kilometer or two away, we have all this growth and things are not eaten. And trying to unravel that, there's probably some genetic or chemical signal in there, but perhaps after listening to Fred and thinking about some behavioral things and some things that animals perhaps were trained by their parents over time to forage in certain areas. Now that, I don't know, I'm just sort of searching here. Comments from either one of you on that?
Good.
Again, as Frank was mentioning, I think that's such an intriguing area to look into, Paul, that whole deal. But I can certainly see that there could be differences in chemical characteristics of the plants in different clones. I can also see that the context those clones are embedded in relative to what animals have learned to eat in terms of how they've learned to mix their diets and the ways that they've learned to do that. All those kind of things could influence the degree to which a clone is used. I don't know, does that make sense?
It starts to make sense, and just the proximity there is what's really sort of fooling us. Why wouldn't you just walk down the block, so to speak, and forage there where there seems to be plenty of forage and high nutritional young growth?
Maybe let me take a shot at it.
Predation could also be a part of that.
Could be predation risk.
Predation.
Animals like to return to the sites where they foraged previously. And there are nutrient inputs by them. It may well be these are more nutritious, and that could be sampled. It may well be that the browsing is causing regrowth of stems that aren't as well defended. We know that in some systems, if it's not too heavy of browsing. But Fred's point about animals kind of sampling is what I used to call it. An ecosystem is true. I worked with an elk population in Northern California that mowed down vast patches of bracken fern. That's supposed to be poisonous. And I watched them forage, and nobody ate much bracken fern. They just come along, and every once in a while there was a high population of elk, and they take a bite. Pretty soon they pretty much mowed down the bracken fern. And so I see exactly the same kinds of things you were talking about.
So Paul, any and all of those things, they aren't mutually exclusive. They could all be influencing that. To me, I just think it would be a great system to start to look at from some of these perspectives and to tease apart some of the mechanisms that are involved in the dynamics of that, with the idea of then how one can start to work with that behaviorally to get whatever response that you want.
I was really hoping you would have the answer.
I thought I just gave it to you.
But complexity is there again, right?
Yes.
And we can unravel these things then.
Yeah.
There was a question over here, Fred.
Yes, Secretary. So, in most of your slides, when you looked at declines in population, it was by, either by drought or by predator. But in a lot of the systems where we have elk numbers increasing, we don't have a lot of large predators. Well, in some areas we don't have them in the system. So have you looked at culling or hunting and how that affects their behavior and their use of cover and aspen?
Yeah, there are data on that. First, I should caution you that even though you don't have large predators now, hold on, they're coming. In fact, wolves have already colonized the Wasatch Front, whether you know it or not. So, but Dale McCullough's work was exactly that, where he let the George Reserve deer population rise to very high levels and then shot it back over a series of 15 years, where he actually attempted to eliminate all the deer. And his estimate was he got down to 10 in a population that was 180 initially, and then recovered over 200 in the next experimental process. So yeah, culling can provide all of those interactions, but I'll caution you that hunters don't select animals the way that predators do, and there may be some differences there. Predators will indeed concentrate on young, given the opportunity to do so. It doesn't mean they just take the old and the sick and the infirm. There's studies from Alaska that show they're perfectly capable of taking completely healthy individuals. But yeah, you get those same benefits relative to forage production and nutrient cycling and those things from culling animals. Yes.
Do you get what's the difference in behavior patterns?
That's a good question. I'm not sure. I think that it's clearly... Oh, I'm sorry. The question was, what about behavior patterns? And I'm not sure, but certainly that's what happened to musk oxen. We invented black powder muskets, and people would approach these big herds of musk oxen on the Arctic coastal plain, and they get in a great big group in a defensive posture, and that was probably the worst thing to do for a hunter, but a really good thing to do if you were confronted by wolves or grizzly bears. So yeah, there's going to be some behavioral differences, I think, but I can't describe to you exactly what they should be. Yeah.
Jerry, are there any studies on the population overshots coming down the low cave, crashing, recovering? Are there any studies on feral horses?
The question is, are there good studies on feral horses of overshoots of K and decline? And I think Duncan has some from Europe. Okay, but it's not immediately coming to mind which of those that is. And Mark Boyce and Eddie Merrill at the University of Alberta are currently working on Lyme predation on on stallions, wild horses in that boreal ecosystem. And so if somebody were going to have that information, I'd email Mark Boyce. But I can't give it to you right off the top of my head.
In the back there?
Fred, you mentioned ECP was after the ice age. And in there, he makes the point that we're headed into another ice age eventually. And I was thinking about that when you were talking about the exotic plants, you know. If you figure out, I mean, if the geologists are correct and whatnot, the historical people, that we are headed into an ice age, so then why are we worried about global warming in the short context, if you can see what I mean? Well, you know, I think the same thing about, you know, natural change in vegetation, where you have invasions of exotics into systems that haven't been influenced by humanity. But when you're talking about stuff like star thistle and spotted knapweed and whatnot, and sheepgrass for that matter, that seriously invades and reduces biodiversity and is anthropogenically induced. I think you have to distinguish between natural change and rapid environmentally induced change.
Yes, so I agree. And as I was mentioning there in the presentation too, I think from the standpoint of the efforts of people that we've worked with, the thrust has been for some of the invasives that really are reducing biodiversity and adversely, from a human standpoint, influencing systems, either from a domestic animal standpoint, through changing grazing management, or specifically targeted grazing, like Kathy Gold is traveling around this country on livestock and landscapes and training animals to be weed eaters. Domestics can be a powerful part of the process of rejuvenating those landscapes. So I agree totally. You know? So when I talk about change and invasives and so forth, I guess what I'm trying to say is that, you know, change is inevitable, of course, and rapid change can be more problematic than change that occurs more slowly. But it is inevitable, and so we need to play the game, right, the here and now. And in the case of those kind of species, why all the work that's come out of our program is looking at trying to reduce their abundance to enhance the biodiversity of those lands. Is that fair enough? In terms of what
you said can be taken out of context pretty fast, though. Just as the global warming issue is being politically abused very badly at this point in time. That's why I raised the issue. We just simply have to distinguish between what we are doing and to our environment and what happens to it naturally.
Sure, yeah. Good point.
Okay, we're going to cut it off there. The food has arrived. I want to give both of our speakers a round of applause. Their two-story top.